Isn't it nice when things just work?
There's a blurb that goes with that little video. There are no computer graphics or digital tricks in these images. Everything that you see happened in real time exactly as you see it. The recording required 606 takes, and in the first 605 takes, there always was something, usually of minor importance, that didn't work. It was necessary for the recording team to install the setup time after time, and it took several weeks working day and night to achieve this effect. The recording cost $6 million, and it took 3 months to finish, including the engineering design of the sequence. There were only 6 Honda Accords built by hand in the whole world, and to the horror of Honda engineers, the recording team disassembled 2 of them for the recording. Everything you see in the sequence, besides the walls, floor, ramp, and untouched Honda, is part of those 2 automobiles. The voice is that of Garrison Keillor. That's probably where most of the $6 million went. The commercial was so well received by Honda execs when they saw it that their first comment was how amazing the computer graphics were. They almost fell out of their chairs when told that the recording was real without any graphics of manipulation. So what you're seeing there is what we call a Rube Goldberg machine, where you try to accomplish some simple task, in this case, pushing that button, with as many energy transfers as possible, make it as complicated as possible. And for many years, I would serve as a judge for the Science Olympiad in Montana, where all the high schools and junior highs would send teams. And one of the events was building a Rube Goldberg machine that would accomplish some simple goal in as complicated a way as possible. And so I hope that while you watch that, you were able to see energy transfers, the kinetic energy transferring into gravitational potential energy and chemical potential energy, different types of energy. Let's start the right way. Would someone be willing to give us an opening prayer? Is anyone ready to pray today? Thank you. In the back, coming up your way.
Our dear Heavenly Father, we thank Thee for this day, and we thank Thee for all the many blessings that Thou hast given us, and we thank Thee for this wonderful opportunity that we have to come to school to learn and to grow and to be able to progress and continue to understand that which we have talked about. We're grateful for our professor, for his enthusiasm and his love for this class and for the students in it. And we ask a blessing upon him and his wife and his family. We ask that we be be able to understand the concepts talked about in today's class. And we give thanks for all that we have, and we do so in the name of thy Son, Jesus Christ. Amen.
Amen. Thank you. Okay. Today, I'm really excited because I get to show you where these formulas come from. And it's going to be simple. It's not going to be some drawn out math class. But first of all, let me just quickly review where we've been, just really fast review. You remember that if we push in the same direction something's going, we increase the energy. And if we push in the opposite direction that it's going, we decrease the energy. And if we push in a direction perpendicular to the way it's going, we don't change the energy. And that gives us a very complicated definition of what we call Verk, what I call Verk. And that's just that it's got this threefold definition. It's positive force times the distance if those are in the same direction. It's negative force times the distance if they're in opposite direction. And it's zero if they're perpendicular. And we talked about this last day. That's very different than the work you get paid for in your job. And that's why I'm calling it something different, Verk, just to distinguish between what you're familiar with and the physics work. Okay? Now, we found that we needed another bucket, and I introduced this concept of a spring being able to do damage. That's what energy is, the capacity to do damage. And that energy or capacity to do damage is 1/2 times the spring constant, how stiff the spring is, times the distance that it's compressed or stretched squared. So you can see that's always going to be a positive quantity, always going to be positive. Now, we left off last day with this simple example where a 10-kilogram block was up against a spring, and we compress, by we I mean some Superman, compresses the spring by 1/2 meter. And its spring constant is huge, 16,000 newtons for each meter. Okay, really, really strong, powerful spring. Now, we were first asked, how much energy is in that spring? And this is just plug and chug into the formula. Now, if I could just pause for a moment. Up until now, I've given you all the formulas that you've needed on the front page of the exam. I'm not here to see whether you can memorize formulas. That's not what I think physics is about. But when it comes to energy, I find that if you don't know these formulas for kinetic energy, gravitational energy, spring energy, you're not recognizing the players on the field. It's like me watching a soccer game. I don't know what's going on. Okay. And so if you don't know these players, the problems aren't going to make sense to you. And so for that reason, and because I love you, I'm not going to give you those equations on the front page of the exam. And there's no one, no, I'm not. And there's no one over at the testing center that's going to give them to you. So you have to have them memorized. And if you have to have them memorized by the time you get to that exam, you just as well do it today. It'll make your life so much easier. Okay. And believe me, it's not like I'm asking you to memorize all 12 bones of the body. Okay. You people are going to be doctors, right? Okay. Now, so I plug into this formula, 1/2 times K times the stretch or compression squared. Remember to square it. And we got 2,000 joules, okay? And so that means in my total energy bucket, I have 2,000 joules. Because the block's not moving, so this bucket's empty. We're calling that level 0, so this bucket's empty. So this is all the energy. Okay, and then we release the block, and we ask, what's its kinetic energy when it gets to point A? Now, again, I remind you, these hash marks mean friction. When there's no hash marks, that's a frictionless surface, okay? Now, the way we solve this is just to say, hey, I had 2,000 joules and I didn't get mugged. I didn't get robbed. I still have 2,000 joules. It's just now it's in the kinetic energy bucket, okay? It's that simple. It's just, where did we put it? Now I can ask, what is the speed of the block at point A? And here I can use that definition of kinetic energy, 1/2 mass times v squared. There's the 2,000 joules, that's my kinetic energy, 1/2 times the mass times the speed squared. And I solve for that and I get 20 meters per second, okay? So far, so good. That's where we've been. That's boring. That's so last week, okay? Now, that block hits the rough patch, and we want to know how far will it slide before it stops, okay? Before it stops. Now, in order to answer that question, we need to use what I call the Verk energy theorem. And you remember this problem we had with the block on wheels where we pushed it for 2 newtons for 10 meters, and we found this equation. And we found that this over here was what changes the kinetic energy. If this were 0, these would be the same. And so I call that the Verk, and I'm going to write it like that. And now I'm going to rearrange it. I'm going to take this initial kinetic energy that's negative and put it over on the other side of the equal sign and make it positive. And then I'm going to take the left side and switch it with the right side, and it looks like this. Now, this is the way you read this. The kinetic energy in the morning is always equal to the kinetic energy at night, except when it's not, and it's usually not. Whenever there's Verk done, it's not, okay? Now, in this problem, this sample problem, we only had one bucket, one kind of energy. Well, what if I've got other buckets? What if the problem's a little bit more nuanced? Well, in that case, I can show that the Graham-Tie equation is this one here, that the total energy in the morning is equal to the total energy at night, except when it's not. Now, folks, that's the starting point for every single energy problem. If you were to take a piece of paper and write that at the top and Xerox that 20 times, you'd be ready for your homework. Every homework problem, you just rip off that top sheet and you're halfway done with your problem. So that's how you start every problem, okay? Every problem. So let's do that. I started with 2,000 joules when it reached point B, and then it scrapes. There's negative Verk done by the friction, and it scrapes until it stops, so I have 0 joules, okay? Now, that Verk is done by the friction force. How big is the friction? Well, anytime I'm looking for a force, I need a free body diagram. And as I've been working with students in my office, I find that many of you are trying to solve our problems on the homework without drawing a free body diagram. And that's just never going to work for you. You can keep trying it, you're adults, but I've never been able to make it work. So if the weight is 100 newtons and there's no acceleration up or down, the normal by the floor is 100 newtons, and this is going to be that coefficient of kinetic friction times that normal force, or 20 newtons. So this equation here looks like that. I started with 2,000 joules, I ended with 0 joules, and that's because the friction of negative 20 times the distance of delta x bled away that energy. Okay, So that gives me an answer of 100 meters. See if your neighbor knows where that came from, can follow that. Yes,
Where did you get the 20 newtons times delta X?
what's that?
Did you get the 20 newtons times delta X?
Oh, right there. Because the friction is to the left and it's moving to the right, we have negative, the Verk is negative force times the distance. Okay?
That's what.
Now, I want to point some things out. 20 meters per second is 40 miles an hour. And yet this block slides 100 meters, a football field. That tells me that 0.2 is a very, very small coefficient of kinetic friction. This is a pretty slippery surface, okay, relatively speaking. Now, just by show of hands, how many of you, when you hit the brakes during the winter on an icy road, how many of you hear a machine gun going off? Raise your hands. Okay, these are the people who have parents that love them, okay? Those brakes, what they're doing is the calipers are grabbing the disc and pressing until it feels like you're gonna start sliding. And then it lets go. And then it grabs again and presses until it thinks you're gonna slide. And then it lets go. And it keeps doing that really fast. Because we know that once you start sliding, you're in trouble. Okay? The static friction is so much better for stopping than the sliding friction, the kinetic friction. And so if you don't hear that, you need to have a heart-to-heart with your parents and just ask them, why don't you love me? Okay? Find out if your neighbor has parents that love them. Do a buddy check.
You don't necessarily drive on those. A little bit, but they, dad. Canadian, so I trust.
Okay,
I don't know why.
so here's where I get to come clean and show you where these equations for the potential energy come from. And it's going to be really, really simple. All I'm doing is I'm finding a way that I can do work and only fill one bucket. And then I look at how much Verk I had to do to fill that one bucket. Well, the first example, I'm going to start with a block down here, and I'm going to push it up a distance h at a slow, constant velocity. Okay? And when you look at it down here, it's already moving at a slow speed. And it's still moving at the same slow speed up there. Now, if I look at the buckets, I've got a little bit of kinetic energy here because it's moving. If I call this height 0, then I don't have anything in the gravitational bucket. And there's no springs in this, so that's just silly, okay? So my total energy is just that kinetic energy. Now, when I get up here, I have exactly the same amount of kinetic energy going the same speed. But now I have gravitational energy that I didn't have before. So my total energy has increased. Now, by my grand high Verk energy theorem, that means that positive Verk was done. In order to get a small amount of total energy into a large amount, I had to do positive Verk. And it's the hand that's doing that positive Verk. Yes, sir. What's that?
Energy is better.
Energy is not a vector. Energy is a scalar. If there's no such thing as energy to the east or energy to the, it's just like paint, you can put it in a bucket. That's the good news. That's the good news. Okay? Now, let's talk about that Verk. It's just the force of the hand times the distance. Well, the distance is gonna be h. But what about the force of the hand? Let's say this block weighs, I don't know, 50 newtons. If you're going at a constant velocity, are you pushing with more than 50, equal to 50, or less than 50 newtons? Equal to 50 newtons. Zero acceleration means balance. And so that means that this force is going to be the weight, mg, and the distance is going to be h. Well, mgh, do you recognize that player on the field? Yeah, that is the formula I have for filling up the gravitational bucket. And that's how I got it. By just doing the vert necessary to fill only that bucket and no other bucket. And I got the formula. See if your neighbor followed that. Yes.
I was about to, it went too far. I was like,
Oh, you're confusing energy with momentum, and we're going to talk about that starting on Thursday. Yeah. It is a momentum is a vector. Yeah, but energy is not. It's energy can go into other buckets like deforming your car and heating up your bumper and.
I don't know.
Yeah. Okay,
All 50.
questions? Okay, let's try this again with our spring energy. What I've got here is a spring. I bought it from the factory, and when it came out of the box, it was this long, okay? And so when I set this block down here next to the spring is not compressed, okay? And then I push the block slowly to compress the spring to here. And I do it in a very special way. I start from rest, I push it slowly at a constant velocity, and then I stop, okay? Now, if I look at the buckets, let's start over here where I started. It's not moving. This bucket's empty. It's on the floor. This bucket's empty. The spring is not compressed. This bucket's empty. There's no energy. Then we go over here. I stopped it over here, so there's nothing in the kinetic energy bucket. It's still on the floor. There's nothing in that bucket. But now the spring is compressed, and so I have total energy. I went from no total energy to some. That means something, the hand, had to do positive vert. So if I just calculate how much vert the hand did, that would tell me the formula for filling that bucket. Well, let's do that, okay? You remember the formula for work is force times distance. And if I'm pushing at a constant velocity, a slow constant velocity, I'm pushing on the block just as hard as the spring is pushing back on the block. Am I not? Okay. I have to push a little bit harder to get it going, a little bit less to get it stopped. But on average, I'm pushing the same as the spring is pushing. Now, we know that by Hooke's law, the spring pushes by an amount K times delta S, where delta S is the compression of the spring. And I'm pushing for a distance, delta S. And so that gives me K times delta S, or K delta S squared. And that's where we get the formula for the potential energy in a spring. If your neighbor's okay with that. Okay. Any questions? Yes. Oh, the 1/2. You're really gonna beat me up over a half? I'm so close. I'm so close. Well, let's talk about that half. Let's talk about that half. This force of K delta S is the force by the spring, not everywhere, but right here, when the spring is already compressed by an amount delta S. But over here, when I started, the spring's not compressed, and so it's not fighting me. Okay, if I actually were doing this, it'd be just super easy here, and then it'd get harder, and then really hard, and then really hard. Okay. So which force do I want to use? Do I want to use the smallest force or the biggest force when I'm calculating the Varric? The average. And the average is going to be halfway in between. And the average is going to be 1/2 times K delta S. Not K delta S, but 1/2 K delta S. So I don't want that. What I want is the average force times the distance that I push. And that's where that half comes from in the average force. And then I get the formula that we recognize as how we fill that spring potential energy bucket. Thank you. Thank you. Good sir in the back. Give me my exercise. Yes.
The second of that.
Oh, the first delta S comes from Hooke's law. The second delta S is in the definition of Varric, force times the distance that you apply the force. And this, I'm compressing it by an amount delta S. Okay? Okay. And now that we understand the idea of Varric, those derivations were very, very easy. If I'd have done that last Thursday, it'd be painful. Okay. Now, I've got here a loop-de-loop, and let's see. So my question is, if this loop-de-loop were truly frictionless, would the mechanical energy, the total energy, increase, decrease, or stay the same as it went around that loop-de-loop? And so with your clicker, this is our first clicker question. And folks, everyone should get this right. You know, if ever there was a problem that we would all get correct, this would be it. Okay. This would be it.
I don't know.
Watch this video back.
I tried using the marble. They've got a wooden ball here, and it just shot across the room. So I did the Hot Wheels car instead. Okay, has everyone got their vote in? Last call. Okay, if we all get this right, we're going to Disney World. Oh, Saved by the Bell. I couldn't afford to take you all to Disney World. Okay. So why is it there's no Varric done by a frictionless ramp? Well, a frictionless ramp can only push on in this case, a car with a normal force. And a normal force by definition is perpendicular to the track everywhere. The motion by definition is parallel to the track everywhere. And so that force and that displacement are 90 degrees with each other. And that, by our definition of physics Varric, gives me 0 Varric. And hence the energy doesn't change. Okay? Now I have an old exam problem, And I need helpers to hand this out. Where are my helpers? Thank you. Thank you very much. Helpers on this side. Thank you. Okay.
I should have.
Send it down that way.
Every time.
Next.
Like passing the sacrament, we got to go back to the other side. Oh, these people still need it. Yeah, just give them a stack and collect the loaves and fishes afterwards. Yeah.
Oh. That's the letter do of the.
Yeah, the friction, right. In this case, I was doing it on a frictionless surface, a floor. And so the only verc being done is by my hand. Then I'd have to put another term in. Yes. It wouldn't go in here. It would go in a separate minus the friction times the distance. Thank you. Thank you. Okay. So in this problem, a block of mass 10 kilograms slides from rest down a frictionless ramp such that the center of the block drops a distance of 0.8 meters. As the block passes from point B to point C, it encounters a 2-meter section of track that's rough, having a coefficient of kinetic friction of 0.3. After passing point C, the block compresses a spring and comes to a momentary stop. In the questions that follow, consider the block or spring system. Assume G is 10. Okay. Let's do this. Gonna get some space here. The first question, find the work, notice we misspelled it there, should be verc, if any, done by the ramp on the system as the block moves from point A to point B. Now, when this was on an exam, that was only worth 2 points. And most people just got 1 point because they said, well, it's 0, okay? But they didn't give the reasoning. And the reasoning, of course, is that the normal force by the track is always perpendicular to the motion, to the displacement. And so there's no verc done by the track. Now, when we get to part B, this is where my class almost lynched me, okay? And that's because on the key, I wrote, on the key I wrote for part B, I wrote, well, first of all, the question is, find the kinetic energy of the block at point B. And I wrote, the kinetic energy at point B is equal to the mass times G times the H. And my students came unglued. Greg, you lying sack of spit. You told us the kinetic energy was 1/2 mv squared, and then on the exam, suddenly it's mgh. What went wrong was I left out a step. What I should have said was that the kinetic energy at B was equal to the gravitational energy at A. which was equal to the M times the G times the H at A. Okay? Why are those equal? Because it's a frictionless track. You just said in part A that it didn't lose any energy. So whatever it had at point A, it still has a B. It's just in a different bucket. Does that make sense? That speak to your soul? Okay. Now, the next question that we're asked is find the magnitude of the friction force on the rough section of track. Well, anytime you're looking for a force, you draw a free body diagram. The weight of that block is 100 newtons. Because there's no acceleration up or down at point B, or at the friction area, the normal by the track on the block is also 100 newtons. The friction force is kinetic friction. And so that's going to be 0.3 times 100 newtons, or 30 newtons. Okay? Now, we're asked to find the kinetic energy of the block at point C. Well, we have that grand high energy Verk equation, and that tells me that the energy initial is equal to the energy final, except when it's not. Now, I want to know what the energy is at point C, so I'm going to make that my final event. And it doesn't matter whether I make this A or B, either way, it's going to be 80 joules. And I'm looking for the energy at C, and I know that all of that energy at C is going to be kinetic energy because it's on the floor and the spring's not compressed yet, okay? So what about the Verk done? Well, the Verk done is going to be negative Verk because the friction is pointing to the left and the block is moving to the right. And so that's going to be negative. There's my friction, and there's my distance was 2 meters. And so essentially, I started with 80 joules, and I was robbed by 60 joules, and that gives me 20 joules, which is the kinetic energy at C. Okay, so visually, I started with 80 joules. I still had it when I got to B. I got robbed by 60, and so I had 20 left. Okay? Now you see how problems that look complicated at first, that look messy at first, are really very easy? And that's because I can make tracks that have loop-de-loops and twists, and as long as they're frictionless, I'm not losing any energy. Okay? Now let's look at this last question. If the spring constant is 160 newtons per meter, how much do we compress the spring at the turnaround point? Okay, well let's call that over here E. Again, I start with that grand high equation. Okay, and I'm looking for the compression at the turnaround point, so I want that to be one of my events. And if I don't want to deal with that rough patch again, it's going to be easier if I choose my initial event to be point C. Okay, because it's already past the rough patch. I don't have to deal with that Verk anymore. And so the Verk in between C and the turnaround point is 0. Well, at C, I had 20 joules. My energy at the turnaround point, I got to stop to turn around, so there's no kinetic energy. I'm on the floor still, so there's no gravitational energy. It's all spring. And it's going to be 1/2 times the spring constant, 160 newtons for each meter, times my delta S squared. So I just solved that for delta S. I multiplied by both sides by 2, I get 40. If I divide 40 by 160, I get 1/4. is equal to delta S squared, and that gives me a delta S of a half meter. Check your neighbor, see if your neighbor's still doing okay. Was that a hand up? What's it? Yeah.
Just a question about the spring. The spring being.
Ah, you hold that question for just a moment. I'm going to cover that question. That's a wonderful question. That's a profound question. Okay. Okay. I want to point out that I could have danced this problem backward. In other words, I could have written it this way. A block of mass 10 kilograms slides from rest down a frictionless ramp such that the center of the block drops a distance h, where we don't know what h is. But then the block passes over this 2-meter section of friction. After passing point C, the block compresses a spring an amount delta S half a meter and comes to a momentary stop. Find h. Well, again, I'd just say my energy at A minus my work done by the friction is going to equal the energy at the turnaround point. I know all the energy at the turnaround point. I know how much energy was lost on the friction. I can find h just by working backwards. Okay. Now, this is a homework problem, but in 1998, it was the first problem on our exam. I was team teaching with my friend Jeff Adams, and we put it as the first problem on the exam because we were convinced in our hearts of hearts that everyone would get it right, and it would boost the confidence of the class and help them do well on the exam. It was a disaster. We would grade late into the night till 3 in the morning, and it was just everyone was not only was everyone getting it wrong, but everyone was taking 35 minutes to do it, and they didn't have time for the rest of the exam. Bad, okay? Well, you've got Tarzan swinging from a ledge that's 5 meters above the lake. The rope is fastened to a tree limb that's 6 meters above the lake's surface. When Tarzan lets go, he has risen to a height of 2 meters above the water. How fast is Tarzan traveling just before he hits the water? Now, quick question. Is energy conserved in this problem? True or false? Energy is conserved. With your clicker, let me get you started. Okay, now you can click. Okay, last call, please. Not rocket science. Rocket science we're starting on Thursday. Okay. Good. It's true. It's true. Okay. It's true if you ignore air resistance. Okay. And that's because a Tarzan vine always pulls along the vine. And Tarzan is always swinging in a direction perpendicular to the vine. And so as he swings, the vine is doing no work on him. And so the energy is conserved. Okay. Now, let's use buckets here. Initially, he's just standing there, so he has no kinetic energy, but he does have potential energy, and that's the total energy. Now, if that total energy is conserved, and we just said it would be, when he gets here, he has some kinetic energy, and he has less potential energy than he started with. Now, again, if we ignore air resistance, all of that energy that he started with, he still has. But now it's all in the kinetic energy bucket because we're calling this height 0. Now it's important that you don't let him hit the water, okay? When he hits the water's doing negative Verk on him, then energy is not conserved. But right before he hits the water, all of that energy is in the kinetic energy bucket. Now here's the big takeaway from this problem. It don't matter what happens in between the initial and the final. And you get to decide what you mean by initial and final, okay? He could do a triple flip with a twist. It don't matter. That's just out of there. And so now I can write my equation, initial energy equals final energy. Initially, I've got potential energy, mgh. At the end, I just have kinetic energy, 1/2 mv squared. The mass cancels, and I just get a very simple answer, 10 meters per second. It's so simple. So why did my students get it wrong and take 35 minutes? Because I gave them that 2 meters there, okay? And suddenly they thought they needed to use that. So they used energy to figure out how fast he was going right there. Then they used some very complicated trigonometry to figure out what angle he was flying at. And then they just turned it into a projectile motion problem. And the whole thing was just a mess. It was a nasty, nasty problem, okay? Don't let that happen to you, okay? Again, when you take the MCAT exam as doctors, they're going to give you information that's not useful and see whether you use it or not. That's not useful, okay? Check to see if your neighbor is going to do well on the MCAT. Okay. So which person strikes the water with the greater speed? Shout it out.
Same.
The same. But this person is having more fun. This person has no idea what they're doing. Okay. Now, a very important question was asked a moment ago, and that is, well, in that old exam problem, what about the Verk done by the spring? What about the Verk done by the spring? Let's talk about that. We have 3 buckets so far. We've got the kinetic energy bucket, the gravitational bucket, and the spring bucket. We add those together to get the total mechanical energy. But when can we talk about all of those buckets? Okay. If we take the block to be our system, if we draw our red circle just around the block, which of these buckets can we reasonably talk about? Well, we can talk about the kinetic energy bucket because that bucket can have velocity or speed, 1/2 mv squared. But we certainly can't talk about spring energy because that's not in our system. That doesn't belong to our system. And so we can't use that bucket. But what about the gravitational bucket? Well, it turns out that this mass has capacity to do damage, energy, because of its location relative to the Earth. The Earth is pulling on it and it's pulling on the Earth. And so you're worried, right? Okay, should be, if I drop it. But if we were in deep outer space where the Earth wasn't there, I'd let go of this and it'd just float there. There's no capacity to do damage there. So this gravitational energy only exists if we include the Earth in our system, So that means I can't talk about either of those buckets, only the kinetic energy bucket. And so let's look what happens to the total energy as this, in this case, the block is attached to the spring. And we're going to compress the spring, and then we're going to release it. And when the spring gets there, when the block gets there, it's got kinetic energy, and there's total energy. When it gets to the spring's equilibrium point, that block's going the fastest it's ever going to go. And I've got a lot of energy. And then the spring starts to stretch and it slows the block down. And I have a little bit of energy. And then I get to the turnaround point where the block has to stop to turn around and I have no energy. Okay? And now as it comes back, goes back and forth. And you see that that's messy, okay? That energy bucket is filling and then it empties and then it fills and then it's emptying. And that's because that spring is sometimes doing positive air, putting energy in, and sometimes it's doing negative air, taking energy out. We don't want to deal with that. The work done by a spring is complicated. So let's include the spring in our system. Let's draw our red circle to include that spring. Well, now, of the 3 buckets, I can talk about 2 of the buckets. I still haven't included the earth, but that's not really important because it stays on the floor, okay? Now, if I go back and, oh, I'm so sorry. You can probably sue the university. You're a rich man. Yeah, I just broke your foot, okay? If I release that block, initially all of the energy is in the spring. And then the spring starts to relax and the block starts to move. So I have less energy in the spring bucket and some in the kinetic energy bucket. But my total energy is what I started with. And then when I get to the equilibrium point, all the energy is in the kinetic bucket. And then it starts to slow the block down and stretch the spring. And then it gets to the turnaround point where all the energy is in the spring. But watch what happens as it goes back and forth. That total energy bucket doesn't change. And that's something I can work with to solve problems. That's simple, okay? And so what that's telling me is that if the spring is part of my system, I never have to worry about the work done by the spring. That's already taken into account, okay? Likewise, if I include the earth in my system, I never ever have to compute the work done by the gravitational force. Never do, okay? Now, if I go back to this Grand High equation, the energy work equation, I want to point out that I lied to you. This is not the right equation. Watch, this is the right equation. Ha! Okay? It's only external work that can change the energy of a system. Only external agents can change the energy of the system. If I had a great big skateboard and I were to sit on that skateboard and push on my back, I'm not going anywhere. That's one part of my system doing work on another part of my system. That's internal, okay? It's only if I push on something outside of my system that I'm going to speed up. That makes sense? Okay. Now, what should we include in our system? What should we put inside the red circle? Well, this is my suggestion to you. Always include everything with mass that's moving so that you can talk about the kinetic energy of those objects, okay? Secondly, always include the earth, by which I mean the gravitational force, so that you can talk about gravitational potential energy, and you'll never have to worry about the work done by the gravitational force. And lastly, include all springs in your system so that you never have to calculate the work done by a spring. It turns out that the work done by a spring changes as the spring stretches or compresses. The more it's compressed, the more it pushes. And so the more work it does. And so you don't want to mess with that. Most times it requires calculus. And we can avoid that just by putting the springs in our system so that that's an internal force. Now, what are the external agents that we leave outside of our system? Oh no, not them, not them. Is that even James Bond to you? Or is it one of these guys? No, that one's mine. Which one's yours? Tell your neighbor. Are you too young to even know what James Bond is?
I know the Daniel Craig ones.
Okay. So we took my wife and her siblings to this James Bond movie, and afterwards the guys were just all excited. Oh man, my wife says, "What, you like that?" No, no, no. Okay. Okay, what are the external agents that are outside of your system? Well, first, go ahead and leave Tarzan swings and frictionless ramps outside. It costs you nothing. They do no wear. Okay, so you just well leave them out. The floor usually does negative wear through friction, and you leave that out of your system because you want to. That's easy enough to calculate. And the energy due to friction, that's thermal energy, that's all sorts of messy. You don't want to deal with that. The lobster hand, which is the only kind of hand I can draw, sometimes does positive Eric, sometimes does negative Eric, depending on how it's pushing. But you leave that outside of your system. And indeed, anything else that's not something with mass moving, the earth, or the springs, leave it outside of your system. Okay? Do a quick buddy check with your neighbor.
Those only cause no.
Okay.
Friction.
If you turn the page over, what you find is the last problem in this week's tutorial homework. And I'm going to show you how to do that problem with the remainder of our time. Okay. What we have here is a simple pendulum that's made up of a string that is connected to a ball that we call a bob, the pendulum bob. I don't know why it's called that. Okay. And let's pretend that this thing is attached to the side of a barn. Okay, it's attached right there. And if we let this bob go, it's going to swing down next to the barn, and it would come over here, except that we've stuck a nail out of the side of the barn. And so when the bob and the string come swinging down, the string hits the nail and it causes this ball to wrap around the nail. Okay, is everyone seeing it? Everyone seeing what's going on there? Okay. And we're looking for some information when this bob, the ball, gets right there. How fast is it going? What's the tension in the string? What's the acceleration of the bob? Okay, those sorts of things. Well, how do we solve that? Well, first of all, we decide on what's our system. Well, you remember how we decide. First of all, we include the ball, the bob, because it has mass, 0.2 kilograms, and it's moving, okay? We include the earth always so that we can talk about gravitational potential energy. And there's no springs in this problem, so that's just silly, okay? Now, if I look at this bob at some arbitrary location, and I draw a free body diagram for it, I always put the weight force first by the earth on the bob, okay? Then I ask, are there any magnets? No. What touches that bob? Well, the string. Does it push or does it pull? It pulls with a tension force by the string on the bob. And that's my free body diagram. The next step is I ask which of those forces are internal and which are external. Well, this is a force by the earth on the bob. Those are both in my system. That's like me pushing on my back, okay? That's internal, okay? The string, however, that's a Tarzan swing, that's external. But because it's a Tarzan swing, it does no Verk. Does the external force do Verk? No. So, is the mechanical energy of the earth ball system conserved from T0 to T top? T0 to T top? Well, yeah. If the only external force does no Verk, there's no external Verk. And by our grand high equation, if this is 0, energy initial is equal to energy final. So now we can start solving your homework. If I want to know how fast it's going right here at the top, and let's use these numbers. You're going to have different numbers in your homework. But let's say that the string is 7 meters long. It's a big pendulum. And that this nail is 6 meters below the pivot, okay? That means that this circle has a radius of 1 meter, does it not? If this is 6 meters, and when this comes all the way down to here, that's 7 meters, that means this right here is 1 meter. So it's going in a circle that's 1 meter in radius. Okay, so really quick with your neighbor, find the speed of that ball at the top. Find the speed of the ball at the top and then use your clicker. You can do it.
Oh, you're right.
The kinetic energy plus the potential energy at the top. Because if you call the lowest point 0, when it gets to the top, it's still 2 meters above the 0. Potential initial is equal to kinetic final plus potential final. You're welcome, anytime.
It's only.
Speeds up. Oh, is that 2 meters? Energy and the energy. It's the loss. It's
Wait.
Yeah, I was like. I think that's the-
Yeah. Cheers. Just run a lot. It would be. Yeah, it's gotten better. And then it's had this little.
Is it at?
Okay, in the interest of time, if you haven't voted yet, just vote for something to get your attendance points. And then we'll work it together. Okay? Still a couple of you. There we go. There we go. Okay. Last call. Oh, we're not sure. Okay, we're all over the map. Well, if I call the lowest point in the problem my zero of height, then I'm starting out 7 meters above that zero. And I'm ending up 2 meters above that zero. There's 1 meter and there's another meter, okay? So if I start with energy conservation and I ask what flavors of energy do I start with? Well, it's not moving to start with, I just have gravitational. But when I get here, I am moving and I still have gravitational. So I plug in my formulas and you see that the M is going to cancel out there, okay? Now, this is a problem that you're going to need to deal with, and that's why I put it up there. And that is that M is the mass, that M is a meter, and that M is a meter. And they look the same, don't they? Okay. I probably should have used a capital M for the mass, but I just want you to know that as you're doing your homework, you need to be careful between M's that are masses and M's that are just meters. Okay. Use some different font. Okay. But I can cancel out the M's that are masses. And when I solve this for the V, I get 10 meters per second. Okay. If your neighbor got that right, give him a attaboy.
I. Right. About it.
Okay. Now, because that ball is going in a circle, it has acceleration. We call it centripetal acceleration. And we covered centripetal acceleration right at the end of the last unit. And so we're going to find ways, you see it in your tutorial homework and in your regular homework, we find ways to go back and revisit that centripetal acceleration. In this case, the centripetal acceleration would point down towards the center of the circle, and it would be V squared over R. V is 10, R is 1, V squared is 100 over 1 is 100 meters per second squared, down. The next part of this problem asks us to find the net force at that point at the top, okay? Well, that's just Newton's second law. I take the mass of 0.2 kilograms, I multiply by the acceleration of 100 meters per second squared, and I get 20 newtons down. 20 newtons down. And then the last problem on this test question, it used to be a test question, is how big is the tension in the string? Well, anytime I'm asked about a force, I immediately draw a free body diagram, okay? The first force I put on that diagram is the weight force. Well, if it's 0.2 kilograms, that weight's going to be 2 newtons. My diagram has to screen down by 20. And there's only one more force to put on that diagram, and that's the tension force. And so if the diagram has to stream down by 20 and weight is 2 of those newtons, the tension has to be 18 newtons, 18 newtons. And that's the end of the problem. Folks, all beginnings are hard. Alle Anfangs sind schwer. Okay, all beginnings are hard. But I hope that you're going to find that this is really very straightforward in the physics. It's messy in the math, in the algebra. But that's just algebra. Okay, go somewhere else, people. I'm going to go pick up my wife. Yeah, let me just turn this off and then I'll be ready.